So this video will deal with the generator effect. We will not do anything analytically with the generator effect or what is it, but we will just treat it as from the concept perspective of it. In the early 1800s, Faraday invented the first electric motor. So what happened was that Faraday was thinking that if the magnetic field if the charge is moving in a magnetic field see an effect on it because there is a magnetic force that it is produced, then the opposite will have the same corresponding effect. So he was saying that if the current has an effect on magnetism, then magnetism may have the same and corresponding effect on the current. And he started to work on this and worked very hard on this. However, it was about 10 years of that he finally had the breakthrough. And it's funny enough because actually initially Joseph Henry was the first one to discover this. However, he was a professor, and at that time the teaching responsibilities came first in comparison to the research, so that the paper was not published. But the same summer, he was thinking to publish it in the summer, but then Faraday had the breakthrough in England, and he published it immediately and now became the first man accredited to successfully demonstrate the electromagnetic induction, or that is known as the generator effect. Faraday discovered the generator effect while he was working on an iron ring apparatus, which I can bring a picture so that you. So he found that while the constant current was flowing on the left side, which is the primary coil, then no current was generated on the right side or the secondary current. However, one day he noticed that was a short-lived current in the second coil as the primary coil was being turned on or turned off. So only that fraction of moment when the primary coil was turned on, primary coil, or off, then current was showing into the secondary current here. Now we know what this is. This is the transformators, okay? Okay, so now what he did is that he like the thinking process that he had is that turning on of the current in the primary coil caused the magnetic field to be induced through the iron rings into the secondary coil, which, as you see here, there is no power on the secondary coil. It's just to measure the ampere, the intensity of the current. It was magnetic field induced through the ring, through the iron ring into the secondary coil. And this is a changing magnetic field. So this changing magnetic field that was induced into the iron rings on the moment of the primary coil were turned off or on was generating current in the secondary coil. But if the intensity of the current in the primary coil was not changing, was constant, then nothing was happening on that. So then the key element necessary for the generator was the changing or moving magnetic field. After the experiment, Faraday found out that the iron ring actually was not necessary because the phenomena would occur just with those two coils if they were close to each other. So the magnetic field traveled through the air from the first coil to the second coil. And Maxwell would use this observation to show that light was in fact electromagnetic wave. We will talk about this in later lessons. Faraday discovered the basic principle of electromagnetic induction, and he experienced those three basic situations. So moving wire, first one, moving wire through a horseshoe magnet. Horseshoe magnet. Electrons flow appears, electrons flow appears only when the conductor was moving. Okay. Next thing that he noticed is that the direction of electron flow depends on the direction of the moving of the wire. Depends on direction of moving of the wire. And multiple loops of wire multiply the voltage produced. Multiple loops on the wire will result on multiple voltage. So this is when we have a moving wire through a horseshoe magnet. Okay. The second one is when we have a bar magnet in and out core of a solenoid. Bar magnet in and out of a solenoid. The relative motion of magnet and the coil produces a current. So when they relatively move to each other, either the bar moves toward the solenoid or the solenoid moves toward the bar, then there is a current that is produced. So relative motion bar magnet and the solenoid will produce a current. Into the coil. Okay, and then for the third observation that Faraday saw, or first finding, was that touching an iron core with a coil, with a bar magnet, and then removing the magnet. Okay, touching the iron core coil with a bar magnet and then removing the magnet. So touching the iron core of coil with a bar magnet. And then removing the magnet. So what was noticed on that case was that the electron flow appears only when the core was becoming magnetized or demagnetized. So only when on the process, not when the magnetizing or demagnetizing the core iron, the iron core of the coil, was complete. So when it was in the process of magnetizing or demagnetizing, magnetizing the iron core of the coil. Okay, and then a changing magnetic field produces a current. Magnetic field produces a current. Yeah. So in other words, Faraday's law of electromagnetic induction is saying that a changing magnetic field induces a current in the conductor. Okay, so Faraday's law of electromagnetic induction is stating that changing magnetic field induces a current in a conductor. Okay, so I will bring a picture here so that we can know what. So now, how does the generator effect compares to the motor effect? Let's see the diagram here. This diagram 1. And if the motor effect is applied and the electrons flow from A to B, as it is shown here, knowing that the magnetic field is leaving north going to south, that is created between those two wire magnets, then magnetic force will be up. Okay, so then this is a straight normal motor effect application. Okay, so this is motor effect. Now let's move to a different situation. What happens if we disconnect the power from the wire? So there is no wire now, no electron flow now, but we pull the wire up. So we physically pull the wire up. Then what we will see is that the electrons will flow from B to A, and this is known as the induced electron flow. Okay, this is pretty much is the generator effect. So on the first one, we had the electrons flowing into the wire, and then we see a force that is lifted. On the second one, what we have, we lift the force. Therefore, the wire is experiencing a change on the magnetic field, and then electron flow is produced, meaning that the current is passing through the wire. And this is the generator effect. Okay. Now you may ask and wonder why the direction of the induced electron flow is now from B to A. Because now Lenz, which is a German scientist, was working on the same time and on the same topic as Faraday. He figured out that an induced current flow is in such a direction that the induced magnetic field it creates, that the induced magnetic field that it creates opposes, and this is the key word, the action of inducing magnet field. The action magnetic field. Okay. If you find that statement confusing, you're not the only one. Okay, let's see now some examples on what. And let's go back to this example here and explain why this is happening. So now, when you are moving the wire up here, then what you are doing is you are cutting the magnetic field lines that are going from north to south, because this is what magnetic field is. So you're going, in order to have, always think like this, that in order to have that motion, the electron to move up, the electron should flow from A to B. But we are opposing that, so the electrons will flow in the opposite direction. Let's see some more examples here. I will bring some pictures so that we can explain the Lenz's law from the conceptual perspective, not calculation perspective. So let's suppose that we have a case when we have a wire magnet here, the north is here and south is here, and then we have a coil or a solenoid that doesn't have any power in it. And then we will see now, we will approach north to the solenoid here. And then we will see and figure out what is the current that is induced current that is formed into this solenoid. Now, since north is coming toward the solenoid, then what will happen is that we need a magnetic field that will oppose this motion. And to oppose the motion of north approaching, you need a north pole in the side of the solenoid that you are working on. Okay, so you need north. Why do you need north? Because you need to push that is coming to you north away. And how do you push it? With the same magnetic pole, because like poles will repel each other. So here you will have north, and here you will have south. However, so this is what you need to create here. This north and south in the solenoid is created as a result of the motion of the electrons in the wire. Okay. Now, based on the second rule of left-hander rule, the thumb will tell us the direction of the north, and the fingers will tell us the direction of the electron. So that is telling us that the electrons will move on this direction. Okay, the electrons will move from B to A. But the current, the induced current, will be from A to B, because the induced current is nothing but the direction of the positive charges, which is the opposite of the negative charges. Does it make sense? Now, what you do, the same bar magnet that you had here, you are taking it away. So the motion will be away from the coil. So if the motion is away from the coil, the induced magnetic field will be such way to oppose the motion. Away would want to attract. And what will be attracted to? North or south? Will be south. So here we will have south, and here we will have north. So now, based on, again, on the second application of the left-hander rule, what we would have is that the motion of the electrons will be from A to B. The electrons will move from A to B, while the current, the intensity of the current, will be from B to A. Okay, so it's always opposing the motion in which you are, or what is causing it. Okay. So those are pretty much the questions that you will see in terms of the Lenz's law or induced current into a solenoid. So you always will see that north is coming toward you, so then you oppose it. How do you oppose it? With the same. If south was coming toward you, then how do you oppose it? With south. Then thumb toward the north, and fingers showing the direction of the electron. And if they're asking for the electron, then keep that. If they're asking for the intensity of the current, switch it. So this is pretty much the generator effect, motor and generator effect. And actually with this video, we close all the video series for forces and fields, which is a very long unit. However, it's very fun and very fundamental for Physics 30. I will see you in class.